See how there's only one M header and it clearly states audio. Now we might sometimes also see an additional M header like M equals video, signifying the user agent also has video capabilities and would like to use it. Having established the media type it would like to use, the media options also provide the addresses and the port information the other guy needs to know so that he can route those media packets should he be willing to accept the invitation. Finally, I tend to look at the digits at the end of the media headers. Now these digits represent the codecs the user agent is willing to use in encoding the media before sending it out across the network. In this case, the user agent has two codecs it's willing to use, 8 representing the G711 ALAW codec and 0 representing the G711 MULAW codec. Now in everyday language I read this description as saying something like, should you accept this invitation, please send your media packets to this IP address where I'll be listening on this port. Or in other words, this is where you'll send your media packets to me. And I'm also happy to use either of these two codecs, although I do have a preference. More on this later. The caller user agent puts the plain text of his invite request, including his media options, into an IP packet and sends it out over the IP network to the downstream user agent. Now, one more thing before we move on from the outgoing invite. Bearing in mind the payload is not limited to just describing media options but can be used for other things too, and bearing in mind all these different payloads have different characteristics, some clues have to be given to the downstream user agent so that it can read the content in the right context. In other words, the user agent needs to know which parser to use and how many characters it should read in order to get the whole content. Nothing more, nothing less. So here's another task for you. Switch back to your user agent and look at the invite for two SIP headers that you think give clues to the downstream user agent regarding how to read the payload in the correct context. Hopefully you'll have concluded that a user agent uses the content length and the content type headers to show the user agent on the other side how to read or parse the payload in the correct context. Remember, the content type header lets the other user agent know what parser to use to read the payload, and the content length tells the other user agent how many characters to read, making sure it reads just the right amount, no more, no less. Gosh, we've been at it for some time now and have only just managed to make and send the first request. Hopefully though, you're starting to get a good idea already of how SIP works and what's found in a SIP message and why they need to be there. Let's continue with our call flow and investigate what happens next. So having included his media options and clues in the SIP headers about how to process the message, as we've said, the user agent puts the plain text of the invite and sends it in an IP packet out over the network. In this case, it's directly to the called party's SIP address, peer-to-peer signaling. The downstream user agent receives the request, reads or parses it, and on seeing the request type being invite, knows immediately that someone's inviting his user to a voice call. Notice how the request is received in exactly the same form as it was sent out. The same request URI, same set of headers, and the same payload. A key point here is that the downstream user agent now has the media options of the caller, so it knows what codecs the other guy is willing to use and where to send the media packets. So in summary of this first step, the caller sends out an invite request to the callee, inviting him to talk and providing his media options. Being a very polite protocol, SIP defines that the receiving user agent should straight away respond back to the caller, in the first instance simply to confirm that the request has arrived. So this seems a good place to formally introduce SIP responses. SIP has 6 families or types of response, each identified by a 3-digit number, beginning with digits 1 to 6, 100s, 200s, 400s and so on, each type reporting some different context back to the calling party. The structure of the response is similar to the request in that it has a start line at the top with a status code and a reason phrase, followed by a selection of headers. Now, although this one doesn't need one, some responses will also have a message body, through which, just like the request, additional content or payload can be sent between the SIP devices. Now, before we look together at this 100 trying response, can you take a moment to look at your 100 trying in your own user agent log and compare it with your invite request that preceded it? Use the prompts on the next screen to jot down some of your observations. I'm hoping that you'll note at least three noteworthy things when you compare those two messages. In fact, I'm also hoping that as you study, you'll find yourself asking one or two questions as well. So make a note of those two, and we'll discuss them in a moment. Interesting. Now, what jumps out at me when I look at these messages side by side is that almost all the headers have simply been copied from the request straight into the response, almost, it seems, without any thought. The one that's different is the content length, which is now 0. Why should the content length in the response be 0? Well, of course, it's because there is no payload in the response. This is just SIP's way of saying that there isn't any payload. Besides the content length, the significant difference I hope you spotted between the two messages are the start lines. In fact, it was when comparing the start lines as a newcomer to SIP that I had one of those questions I'm hoping you might have asked yourself in your analysis just now. For me, having worked with SIP for a while, when I look at these two start lines, there are two things conceptually I see common to both, and one thing conceptually that's missing from the response. Can you take a moment and compare for yourself to see if you can find those two things that are common to both and the one thing that conceptually is missing from the response? Here are the three things that I'm thinking about. The bit that defines the purpose of the message, the bit that provides the routing information for the message, and the bit that provides the protocol version. So with the request, it's the method type which defines its purpose, the request URI for the routing, and the bit on the end for the protocol version. In the response, however, although in a different order, we now have at the beginning the bit for the protocol version. And for the purpose, we actually have two things, the status code and the reason phrase, meaning that there is no routing information in the response start line. Nothing in the start line to determine the route for the response to go back from the user agent server up to the user agent client. So that now begs the question, how is the response routed? Any ideas? Well, why not take a look at the response and come up with a hypothesis about how you think the user agent server gets routing information to route the response back upstream? Simple. It's the VIA header. The user agent client puts its own IP address in the VIA header of its outgoing request, especially for the purpose of telling the guys downstream where the response should be sent. The downstream user agent, in copying the VIA header address into its response, remembers to use that address in the routing of the response. So unlike the request, where the routing information is typically held in the request URI in the start line, the routing of the responses are different. It's the VIA header that provides the routing information for the response. I've got to be straight with you. When I found out it was the VIA header that determined the route back for the response and not the start line, I had to wonder why. Well, there's a good reason why, one that we'll deal with later in lesson 3. But as we cover more concepts, I wonder if you can figure out why for yourself before we get there. Another thing I remember questioning when learning about SIP responses was something to do with the to and the from headers. Something puzzled me. Take a quick look again now at your 100 trying and compare the to and the from headers with those in the invite. Are things as you expect them to be? I personally was quite surprised to see the to and the from headers had not been reversed. I was kind of expecting that the to address in the response would show who the response was going to, and likewise the from address would signify who the response was from. Not so. The to header does not mean this is a response to SIP John. The to and the from headers are simply copied from the request straight into the response. They're not changed at all. I always suggest in reading SIP responses that we put things in the context of it being a response to a request. Accordingly, I recommend we read the to and the from headers in the response something like, this is a response to a request that was to John from Dave. Now that we know how the response is routed from user agent server back to user agent client, my next question is, why? What's the purpose of the 100 trying? Well, here's a question for you, one to set the context for this next discussion. Which of the transport layer protocols do you think SIP uses for carrying its signaling requests? Those all-important requests without which the call cannot set up successfully. One could be forgiven for thinking that SIP's default transport protocol would be TCP. After all, one of TCP's qualities is that it takes care of reliable delivery. We just give it some data and an address, and it takes care of the rest. If some of the packets get lost on the way, we don't have to worry about it, as TCP checks what was sent and what arrived, and automatically takes care of retransmissions if something goes wrong. Funnily enough, TCP is not SIP's standard transport protocol. Whilst it's fantastic at taking care of reliable delivery, it just takes too long to set up the connection and to check that all is well with every transfer. SIP prefers instead to use a transport protocol that has much less overhead, one that is much quicker. The default transport for SIP is UDP. Now, UDP receives data from the upper layers, just like TCP, but sends it out over the network without spending any time checking to see if the guy on the other side even exists, never mind whether or not he's ready to receive. Now, this means that it's very quick. However, UDP is a connectionless transport protocol. There are no checks made before or after transmission. If the packet gets lost on its way over, what does UDP do about it? Nothing. UDP doesn't even know or care about the loss. Its job is to send and forget as quickly as possible and not worry about anything else. UDP will not transmit and the packet is lost. So you might be asking, well, what happens to a SIP request then if it's UDP that delivers the packet and the packet gets lost? Well, the answer is that SIP has its own built-in mechanism for reliable delivery of its signaling messages. In fact, it's the user agents themselves that are responsible between them for reliable delivery. Here's how it works. When a user agent sends out a request, it sets a timer for half a second and waits to see if it gets anything back. If the message gets lost on the way, or if there's no SIP device on the other side to receive the request, and nothing comes back before the timer expires, the user agent will assume something has gone wrong and will retransmit the request. At the same time, it will set the timer, this time for 1 second, and wait to see if anything comes back from this one. When the user agent on the other side receives the request, being the user agent of a polite protocol like SIP, it knows immediately to create and send some kind of response. Initially, just for purposes of letting the guy upstream know that his request has been received and not to retransmit anymore. In fact, that's what the 100 trying is for. It says, I have received your request and am now trying to do something about it. You don't need to retransmit it anymore. I have it. The trouble is, this is UDP, and UDP is not having a good day today. The response, perhaps on its way upstream, may also get lost. What do you suggest happens now if the response does get lost? If something happens so the response doesn't make it back to the user agent client, then the timer will expire again. Remember how the user agent reset the timer after the first transmission failed? It'll then do exactly the same thing it did last time the timer expired without receiving a response. Retransmit the request and reset the timer, this time for 2 seconds. The user agent on the other side then receives the request and, on realizing it's a retransmission, simply retransmits the response. If the response arrives upstream okay, then the user agent client heaves a big sigh of relief and says, "Phew, I'm happy now. I know that my request has been delivered reliably. I don't need to retransmit anymore." It's time for you to do some analysis again now, this time on the subject of reliable delivery and retransmissions. I'd like you to figure out a way of organizing things at your user agent so that when you set up another call, it will retransmit the request a number of times. Why not do that now, then press play when you've done it. If you need a clue about how to set things up for retransmissions, press play and I'll give you a tip. If you need a clue, consider the dial-out address that you choose to use in your user agent. So, you've hopefully already done something like enter a bogus address in the dial-out field of your user agent with no SIP device at that address. So, of course, when the request goes out, nothing comes back and your user agent retransmits. So here's how I'll do it. I'll just rearrange the user agents a little bit here, give myself a bit more space. And I'll open up the call tabs so we can see what's going on there. Okay, so I'll just bring up the same address I used last time and click dial. And we can see straight away the call's being set up. I'll accept, and hang up. So I'll clean up, and all I need to do now is change one of these digits here in the address to make an address that does not exist. Let's say we're going to dial out to SIP 192.168.2.2.11 rather than 2.10. Here we go, dial. Now of course there's no user agents on the other side, nothing to receive the request and therefore nothing to send back a response, and we're getting retransmissions. Next, take a look at just the initial invite request, not the retransmissions just yet, and look for the header or headers you think might change to signify a retransmission. Once you've come up with your hypothesis, then take a look at the retransmitted request and check things out. So what differences did you find between the first transmission and the retransmission? There are only a couple of headers we haven't looked at yet together. So how about the CSEC header? Did the CSEC header change at all? No? Oh, well, how about the call ID? That didn't change either. Well, you may have realized by now that actually there was no change at all in the request between the first transmission and the retransmission. In fact, that's how a user agent knows an incoming request is a retransmission. It's exactly the same as one that it's seen already a moment ago. So, when you're looking through log files in real-life situations, perhaps log files with hundreds or even thousands of messages, you know now that when you see multiple repeated messages, it's because something has not responded as expected. Something has not perhaps been delivered reliably, and retransmissions have taken place. It will also be good to study the pattern of transmissions. Find out how many transmissions or retransmissions the user agent makes before it finally gives up, and then calculate the time interval between the first transmission and the last retransmission. So hopefully you'll have found out that if nothing comes back, the invite is transmitted a total of 7 times over a period of 32 seconds. Each retransmission is given a little bit more time just to help prevent clogging of the network and to provide a bit more time in case more time is needed on the other side. Finally, make a prediction about what you think will happen after the user agent has finally given up on the request. Then take a look at the log and check your hypothesis. Remember though, SIP is a very polite protocol. Now regarding what happens after the user agent gives up retransmitting, hopefully you've remembered that SIP is a very polite protocol and as such can't bear the thought of some guy downstream not knowing what's going on. I mean, perhaps there is someone downstream and perhaps they have been receiving each of the requests, but for some reason none of their responses have made it back. So just in case, the user agent client creates and sends a cancel request, meaning something like, hey, you know that request I sent you a moment ago? Forget it. Cancel it. I'm not doing anything more with it just now. Now the cancel request is just the same as any other requests. It needs to be delivered reliably. So my question to you, what will the user agent do now as it sends out the cancel? What will it expect? After sending a cancel request, the user agent sets a timer again for half a second, hoping to receive something back, some type of response, before the timer expires. If it does, it can be happy in the knowledge that its cancel request was delivered reliably and will not need to be retransmitted. It's pretty unlikely, however, that the user agent client will receive a response to a cancel when it didn't receive one to its invite. But that's not the point. SIP is a very polite protocol and it does its best to keep others updated and not hanging around wondering what's going on. I hope you noticed this time, for a non-invite request, there are actually 11 transmissions, not 7, over the same time period of 32 seconds. After this, I think we'd all agree that the user agent has had a jolly good go at being polite and can now legitimately give up, confident that it's done all in its power to make sure that anyone downstream knows this session isn't going anywhere. So what are some real uncontrived reasons that we might see retransmissions in the SIP network? One that I come across time and time again is the issue of firewalls on the machines upon which the user agents are running. Firewalls that don't know about SIP. The user agent client sends out a request and it arrives at the right place but is blocked by this non-SIP aware firewall. So the user agent tries again and again and again, 7 times in total over 32 seconds, but always to no avail. Not even the cancel gets through. The solution is to either turn off the firewall, or perhaps even better, to configure the firewall to allow SIP traffic to go through. And remember, that's by default port 5060. although you may have chosen to use a different port today. Another reason might be something as simple as having made a typo as you enter the dial-out SIP address. Now, although we think we have the right address, if it's not absolutely correct, it's as if the downstream user agent just doesn't exist. So when the request gets sent out, it has nowhere to go and of course will not trigger any responses. The solution here is of course to check the address we dial. Now at this point in our lesson at least, check that what you enter is the same as what's being configured in the downstream user agent's contact address. It won't always be the contact address you'll be dialing though. Later on in the next lesson we'll be using different types of addresses for dialing out. One final reason we'll look at could be some incorrect user agent configuration. It could be that we've dialed out to the correct address, meaning that the request is sent out and arrives as expected at the other side, but because the user agent hasn't been configured correctly, it may have some incorrect content relating to the routing of the response, or even a subsequent request, back upstream. The downstream user agent correctly takes routing information from the request, but because it's incorrect data, the response will be sent to a non-existent location. And although the response was sent, the user agent client didn't receive it, and the retransmission will be triggered. So if you get problems, remember to check that your user agent is configured properly. Okay, I've introduced quite a few more new terms in these last few topics. You know what to do now. Try and verbalize a definition for each one of them, and when you're ready, press play and my definitions will appear. Well, I've been talking for almost an hour already, and with all the practicals and analysis, you've been working for longer than that. How about I summarise now briefly what we've done so far, give you an opportunity to work through some review questions, and then just before we bring the session to a close, I'll tell you what's coming up in the next lesson. So what we've said is the downstream user agent, after receiving the invite, constructs a 100 trying response, copying almost all the headers from the received requests and sends it to the address in the VIA header, back to the upstream user agent client, confirming reliable delivery of the invite request. Now on receiving something back from the other side, the upstream user agent client heaves a sigh of relief, happy in the assurance that its request was received and that someone is trying to do something about it, and that he doesn't need to worry anymore about retransmissions. Now that messages have been exchanged, we can visualize a signaling path between the two endpoints. It's not a private tunnel or anything, it's just a route over which SIP messages can pass between caller and callee. So summarizing the call flow so far, and remember it's this diagram that I'm hoping you'll commit to memory, we see the initial invite request followed straight away by a 100 trying response. So, we began the lesson with some general principles of signaling and media exchange. Remember the guys at their desks and the need to attract each other's attention and agree to communicate before they can start exchanging media? We looked at general principles of voice over IP and how it describes the process of encoding and sending media packets across the network. But we also discussed, however, that voice over IP alone doesn't provide enough detail regarding how the session should actually be established. In other words, how the two parties find each other's location or IP address and which encoders they should use. Now this is of course where SIP comes in. It's SIP that defines the processes and behaviours that enable parties to know what to do to set up that voice over IP session. In fact, SIP does more than initiate sessions, but we haven't really touched on any of those yet. We looked at SIP user agents and how they are the devices we use to set up our calls. Remember how they have two modes, switching between user agent client and user agent server, depending on whether they're starting something or responding to something? We then set up our first SIP call together, and you've begun already analysing the exchange of messages within the call and are in the process of committing the basic call flow to memory. You've started to analyse SIP messages as well, the requests and the responses, and so far we've looked at the invite request, used to begin the initiation of a voice call, and we've looked at the 100 trying response, used to confirm reliable delivery of the request. We've also taken our first look at the cancel request, in the context here of SIP, being a very polite protocol, wanting to let the other party know when it's given up retransmitting a request after not receiving any response. We've made a start looking at headers within the SIP messages. We know that the to and the from headers always give a constant reference as to who the request is intended for and who the request is from, regardless of whether we're reading the to and from headers in the request or the response. Remember how they don't change, they're not reversed in the response. Now I like to think of the from header as saying, This is who I am. The contact header, on the other hand, says something like, this is where I am. SIP uses the contact header to give the sender's address to the other guy so he knows where to route those subsequent requests back upstream. We haven't really done much with the subsequent requests yet, but we'll deal with those in the next lesson. We talked about the content type and the content length headers and how they provide a context for the guy on the other side regarding how to read the payload. In other words, which parser to load up. In an invite request, it's almost always going to need to use the SDP parser. The via header is simply for routing responses back upstream to the caller. Not to be confused with the contact header, even though they both have the addresses of the sender. The via header is for routing responses. The contact header is for routing subsequent requests. We've looked at the payload of our invite and saw how it was used to carry information about the codecs a user agent is willing to use, plus routing information. Not for responses or subsequent requests, but this time for routing media packets. Remember how these media options are defined by a separate protocol? The Session Description Protocol, or the SDP. Finally, we spent quite a long time on the important topic of reliable delivery. We discussed how SIP chooses to use an unreliable transport protocol, UDP, because of its speed in delivery. But we also discussed, however, that because reliable delivery is so important, we can't afford for packets to be lost as they sometimes are with UDP. SIP has its own mechanism for reliable delivery, based on user agents setting timers and retransmitting requests if they don't receive something back before the timer expires. Often that first response coming back will be the 100 trying. We saw how an invite will be retransmitted a total of 7 times over 32 seconds before it finally gives up and sends a cancel request. Right, got all that? Let's see how you do now with these review questions. Great. Coming up in the next lesson, we'll finish off this first peer-to-peer call we've been working on together. We'll get more into the SIP messages and the SIP message flow. We've got more work to do on media options and how the callee's media options now must be returned to the caller. And there's that perhaps controversial issue of negotiating media options to deal with. You know, when clients have multiple codecs to choose from, which one do they actually use? We'll get into more headers and we'll spend a bit more time on reliable delivery, next time focusing on reliable delivery of the final responses. Finally, in the next lesson, we'll look at the fascinating topic of route sets and how user agents keep and use them for routing subsequent requests. Can't wait!